Okay, part 8, and the last part of chapter 13, something called isomers. Now, isomers are when you have the same formula for two molecules, but they have different Lewis structures. And there are a number of different types of isotopes, or isomers rather, but we're just going to focus on the five major ones. And I'm going to start with a conversation of how isomers can be important and how they affect us. So we'll go back to our chapter notes, and they start to talk about something called a saturated compound. Now, when your carbons only have single bonds, we say it's saturated, which means it has the maximum amount of hydrogens that it could possibly have. Now, the carbon to hydrogen bond, especially in the body, is very unreactive. They have very similar electronegativities. An unsaturated hydrocarbon is when you replace a single bond with a double bond, so now you no longer have the maximum amount of hydrogens. But a double bond is an area of high energy, which means it's very easy to break apart in a chemical reaction. So saturated hydrocarbons behave very differently than unsaturated hydrocarbons. So here's some examples. The first one, all single bonds. That would be propane. These things tend to be good fuels, but they're not very good at being what's called builder molecules. In other words, there is no place here for there to be a good chemical reaction. Whereas with the second and third example, what we have is a double bond, and that's very vulnerable to a chemical attack. So we can break that bond there and create new particles attaching to it and create new substances. And the same thing here with the triple bond. And those sort of unsaturated hydrocarbons tend to be, again, what I call builder molecules, that you can build them up into bigger molecules, plastics and synthetic surfaces, Dacron, those sort of type of materials that we use in industry come from these builder molecules. In terms of health, they talk about fatty acids, and there are two types, saturated fats and unsaturated fats. And the difference between them has to do with where chemical reactions can occur. Saturated fats are difficult to break down because the only area of high energy on a saturated fat is over here at the end of the molecule. Now, if you think about particles hitting this and trying to break those bonds, most of the particles are going to hit somewhere towards the middle of the molecule. Very less frequently do you get collisions here on the end of the molecule. So the only way to chemically break down a saturated fat in the body is to hit that end of the molecule, which doesn't happen very often. Whereas in an unsaturated fat, depending upon how many of these functional groups you have, now you have multiple locations where reactions can occur and the fats can break down. So unsaturated fats tend to be healthier for you than saturated fats. Now, saturated fats tend to have an animal source to them. Unsaturated fats tend to be plant sources, but there are some plant sources that have fats in them that are saturated. So, which is healthier, butter or olive oil? Well, again, it depends upon whether it's coming from a plant source or a animal source. Butter tends to be from animal fats, so that's more difficult to break down because they are saturated fats, whereas olive oil has a combination of saturated and unsaturated fats. Besides having the functional group, what they call a functional group is an area of high energy where reactions can occur. Besides having more functional groups, more reaction areas, things with double bonds tend to kink and bend, what we call a cis-trans arrangement. If they bend in a way that spreads things out, we call that trans. So if you have a double bond where things are spread out, you have what's called a trans fat. And if you have them where their chains kink towards other chains, like in the second example here, then you have what's called a cis fat. And cis fats tend to be a lot easier to break down than trans fats. Trans fats, where everything is spread out equally, are more stable, and so more difficult to break the bonds. Whereas if the fatty acid strands kink towards each other, that creates high energy repulsion and is easier to break down. So again, cis and trans fatty acids. So trans fats, again, at the double bond, we have these hydrogens spread out equally. That makes them more stable and more difficult to break down. Whereas with a cis fat, they tend to kink towards other strands, and that makes them easier to break down. All right, so again, functional group. Oh, you just have to know the definition of it. It's an area where reactions occur, high energy areas. They can be double bonds or triple bonds, but they can also be areas where you have molecules of high electronegativity. Alcohols, for instance, have a hydroxy functional group, which is an oxygen connected to a hydrogen. The oxygen is highly electronegative, which makes it very easy to break off of the molecule. Here's some examples of other functional groups. You don't have to know the names of them because we do not have time, and this is not business as usual. So if we had time, I would go through all these and we would learn them. But we could tell that they're functional groups because, again, we have these electronegative elements here, nitrogen and oxygen, where we have this polarity, and it's a lot easier to break things down. Double bonds, a lot easier to break things down because of the high energy pi bonds. All right, last part of the chapter, isomers. When you have two molecules having the same formula but different structures. Now, there's a bunch of type of isomers. We're only going to focus on the 5 major ones. The first one falls into the category of what we call constitutional isomers, where you're taking the molecule and you're changing the order in which the atoms are connected. So these examples, pentane, 2-methylbutane, 2,2-dimethylpropane, I'm going to diagram those and show you the differences. But these would be considered structural isomers. They're a different arrangement in the way the carbons are connected to each other. So in the first one, pentane, all of these molecules have the formula C5H12, but in pentane, the carbons are connected to each other in a straight sequence, and then the 12 hydrogens would be connected to those carbons, filling up the octets. So in pentane, we have a straight, what's called a straight carbon chain, whereas in 2-methylbutane, remember, pent means 5 carbons. But, not but, means 4 carbons. So we'd have 4 carbons in a row. And then meth means 1 carbon. So we would have 1 carbon connected to the second carbon in the straight chain. So now we don't have the 5 carbons go straight across. We have one of them branching off from the other 4. And then here's 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens. And then in the last example, 2,2-dimethylpropane. Prop means 3 carbons. And then we go to the second carbon and we put a methyl group. Now there's 2 of them. That's why they say 2, 2 dimethyl, but we're not doing organic nomenclature, so you don't have to worry about that. Here's 3 hydrogens, 6, 9, 12. So very different properties. For instance, pentane tends to be a very long oval-shaped molecule, whereas dimethylpropane tends to be very spherical in overall shape. And if we were to take pentane molecules and lay them next to each other, they have a lot more surface area where they come into contact, whereas 2,2-dimethylpropane, there's going to be a lot of space in between the molecules and very little surface contact between them. So for instance, pentane is going to have a much higher boiling point because it has stronger intermolecular forces. So each of these 3 compounds are going to have different melting points, different boiling points, different chemical reactivities, even though they all have the same formula, C5H12. So again, that is called a structural isomer, where you're changing the order in which the carbons are connected. All right, second type, positional isomers. There's several types of positional isomers, but I want to focus on just one type. It's the position of a double or triple bond. So 1-butene versus 2-butene. All right, both of these have the formula C4H8, and 1-butene means that we have 4 carbons. That's what the but stands for. And we have a double bond starting at carbon number 1 and going to carbon number 2. And then we have our 2, 3, 4, 5, 6, 7, 8 hydrogens around it. And 2-butene is the same type of structure, 4 carbons, except for now we start the double bond at carbon number 2 and end it at carbon number 3. So here's 3, 4, 5, 6, 7, 8 hydrogens. So different points where the molecule is going to break apart during a chemical reaction, different shapes. So again, different melting points, boiling points, different chemical reactivities, even though they have the same formula. Again, this is called the positional isomer. We're changing the position of where the double bond is. Third type, functional isomer. All right, functional isomer, there's 2 types here. My slideshow talks about the position of a functional group. That's really a positional isomer. Or it could be a totally different functional group. So I'm actually going to do 3 examples with this, 1-butanol versus 2-butanol. And then I'm going to throw in an ether. Okay, so 1-butanol, again, we have 4 carbons. The OL means that we have an OH group attached to the first carbon, and then we put 2, 3, 4, 5, 6, 7, 8, 9 more hydrogens. So the formula is C4H10O. And 2-butanol would be the same molecule, except the OH group is connected to the second carbon. Or you could wind up having a totally different functional group. For instance, instead of an alcohol, you could have an ether where we have 2 carbons and then the oxygen in the middle connected to 2 more carbons. And then we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And this is called ethoxyethane is the IUPAC name, but a common name is called diethyl ether. Now, when you have a totally different functional group, what it means is that it behaves totally differently. For instance, alcohols in industry are used to dehydrate things, where ethers are used as extractants. They dissolve certain crystals and leave other crystals alone. For instance, if you were going to make methamphetamine, don't do that, illegal. But if you made crystal meth, you would extract the crystal meth crystals in ether. They would dissolve in the ether, and then you could filter out all the impurities and, have your crystal meth lab there going. But again, don't do that. A different category other than constitutional isomers, geometric isomers are very common. There are 2 major types of geometric isomers. One where we take a look at the arrangement of things in relationship to a double bond. This is called a cis versus trans, or cis-trans isomer. So we'll look at cis-2-pentene and trans-2-pentene. Cis-2-pentene. Okay, so I'm going to draw it using bond line. If we start with the first carbon and go to the second, then we can create a double bond between the second and the third, and then we have the fourth and the fifth carbons. And this is a cis arrangement. Cis is Greek meaning on the same side. So I have one part of the carbon chain, and then it goes down through the double bond and then returns to the same side. In other words, it kinks towards each other. We would say that this is a cis relationship. Whereas in trans-2-butene, trans-2-pentene, sorry. Again, we start out carbon 1, we go to carbon 2, and we create the double bond. But instead of going back to the north side of the molecule, the rest of the chain goes to the south side. So there's my 4th carbon, there's my 5th. And we would say that this arrangement between the double bond, where you start on one side and you end on another side, is a trans relationship. So different chemical reactivities, because different overall shapes, And the trans, because everything is spread out better instead of kinking back towards each other, is more stable and less reactive. The last type of isomer is called a chiral isomer. And here's the definition, where the two molecules are different from each other by being non-superposable mirror images of each other. Now, the term chirality comes from the Greek word literally meaning handedness. So it's like your hands. If you take your left hand and compare it to your right hand, please do, nobody's watching. Your hand, you have a thumb, and then the next finger is your index finger, and then tall guy, because you're not allowed to say middle finger to elementary school kids anymore, and then ring finger, and then pinky. And if you hold your hands up together, they are mirror images of each other. But if you go to put one hand on top of the other, they don't match up, even though they're the same fingers connected in the same order. On your left hand, if you go from your pinky to your thumb, that is a left rotation. On your right hand, if you go from your pinky to your thumb, you have to rotate to the right to get to it. So left hand, right hand, if you had your hands cut off and you went to the doctor and the doctor said, oh, no problem, there's a bin full of hands over there. If you went and grabbed two left hands and put them on your wrist stumps, then you wouldn't be able to grasp objects. And yes, I know there's a lot of flaws in that analogy. So exactly what is chirality in terms of molecules? Well, chirality describes a relationship between molecules. And it's sort of like, the analogy would be like shaking hands. If you extend your right hand and somebody else extends their right hand, when you shake hands, which we're not supposed to be doing right now, by the way, right? Social distancing. But if you did that, you would have a different sensation than if you extended your right hand and somebody else also extended their right hand. It'd be much more difficult to shake hands that way. And that's sort of the chemical analogy of molecules behaving together, that the right-handed ones tend to react better with other right-handed molecules. Now, none of them are right-handed. They don't have hands. So what we're talking about is the rotation involved in going from either left to right with the way things are connected or right to left. In biology, they don't use the same terms we do in chemistry because they're different. A right-hand rotation we call rectus rotation. A left-hand rotation we call sinister. And the word comes from Latin and has to do with ancient Judeo-Christian beliefs that evil always approaches from the left side. So the word sinister means left. Now in biology, they talk about a right-handed rotation using the term dextrorotary, which actually means it rotates light to the right. And then levorotary rotates light to the left. So you have D isomers and L isomers for right-handed and left-handed. Again, levo is short for Leviathan, which means evil. Again, that Judeo-Christian evil approaches from the left thing. And in chemistry, we have R isomers or S isomers, depending upon whether things are rotated from the right or to the left. All right, so what does that look like, chiral? Glad you asked. Okay, so first of all, these two models represent isomers that are chiral. They are mirror images of each other. Here's another view of it. And they look pretty much the same. However, if you put one in front of the other, I can get the purples to match up and the greens to match up, but you can't get the yellows and the reds to match up. They actually are different from each other. No matter how you rotate that front one, all three of those colors aren't going to match up. Okay, so in this particular isomer, if we look at it from the left, or from the front rather, and let's say that this represents iodine, and this represents chlorine, and this represents oxygen. If we go from the highest mass material to the lowest mass material, we'd have to go from iodine through chlorine to oxygen. This would be a right-hand rotation. So in chemistry, we would say that this is the rectus or R version of the isomer. Whereas with the other one, again, we go from iodine to chlorine to oxygen. Now we're going in the opposite direction. This would be a left-hand or counterclockwise rotation, and we would say that this is the S isomer, the sinister isomer. All right, so what do you have to do on a test? Well, I'm glad you asked. On a test, I would ask you, hey, here's a pair of molecules. What type of isomer is it? So let's try these. By the way, now this makes sense, right? Constitutional isocats, where the tail and the legs are in different places. Again, we change the order in which the limbs are connected. And the Samuel L. Jackson versus Samuel D. Jackson one should make more sense to you now, because they are mirror images of each other, and Samuel Jackson is looking towards the left in the first picture, and he's looking towards the right in the second picture, and the person hopes that it goes chiral instead of viral. These are so funny. Anyway, so pause the video each time, come up with what type of isomer this is. Let's zoom in on it. All right, I'm done waiting for you. So here we have 1, 2, 3, 4 carbons connected in a row. But here we have 1, 2, 3 carbons, and then this carbon is connected to the second one. So we would say that this is a structural isomer. So let's try the next one. Again, pause, give it a shot, see what you come up with. Okay, I'm done waiting for you. This has a double bond starting at carbon 2 and ending at carbon 3. This has a double bond starting at carbon 1 and ending at carbon 2. And we would say that this is a positional isomer. All right, this one. Go ahead and pause. And I'm done waiting for you. Okay, this one we have a double bond starting at carbon 2 and ending at 3. This one, carbon 1, starts at carbon 2 and ends at 3. They both have the double bond in the same position, but this one is kinked back towards itself, a cis configuration, where this one is spread out. The chain starts on the south side, ends on the north side, and we would say that this is the trans relation. So these are geometric, or I would accept the term cis-trans, because there's actually several different types of geometric isomers. Try this one. Pause. Okay, done waiting for you. This is a functional isomer because the oxygen here is connected to the first carbon. This oxygen is connected to the first carbon, but it's also connected to a second carbon. So they're totally different functional groups, where the oxygen is within the carbon chain, and here the oxygen is connected to the end of the carbon chain. This would be an ether, and this would be an alcohol. So they are functional isomers. And then the last one. In order to have chirality, I'm not even letting you pause here, the mirror images of each other, if we pretend there was a mirror here, these would be mirror images, so non-superimposable mirror images. And if we rotate from the purple to the orange to the green, this would be a right rotation. Here, purple to the orange to the green would be a left rotation. Or I guess I should be consistent here. Let's say sinister. So S rotation. So this would be a chiral isomer. And that's it for chapter 13. Thank you very much.